guys. Please look it up. So in the last class, we discussed about static route, default route, and we also discussed about RIP, EIGRP, and OSPF. Okay. In the static route, we saw how to configure your static route. We saw 3 ways to configure your static route. The first one was recursive static route. So in case of recursive static route, we were using the next hop address, right? We said IP route, then we said network ID, subnet mask, and then next hop address. Correct. But while providing the next hop, there was a problem. What was the problem? Recursive lookup means your router has to look in the routing table 2 times. Okay. So in this case, recursive lookup is a problem. This was the issue. Your router has to look 2 times. First time for the next hop and second time for the exit interface. Correct. So we came up with another method that is directly connected. Directly connected static route. So what we did in this directly connected, we directly provided the exit interface instead of next hop. So if we will directly provide the exit interface, what will happen? Your router doesn't have to look 2 times in the routing table to forward a packet. So the command was IP route, network ID, subnet mask, and we finally gave the exit interface. Correct. But again, in this case, proxy ARP was a problem. In this case, proxy ARP is a disadvantage. Why? Because your router considers the networks to be directly connected. Let's say this was 12.0 and this side we have 10, 20, and 30 network. Correct. So when we are defining a route using the exit interface Z0/0, so your router R1 start considering that your 20 network, it is directly connected on the interface Z0/0. So it will just forward the packet on this. But to reach here, your R1 needs the MAC address. Because again, your ICMP packet is going to need source IP, destination IP, source MAC, and destination MAC. And if the information is incomplete, router cannot forward the packet. Correct. So what happens if R2 is acting as a proxy? R2 is going to provide its own MAC address for the 20 network. R2 is going to provide its own MAC address for the 20 network. And then R1 will forward the packet accordingly. But if R2 is not acting as a proxy, R2 is not going to provide the MAC address. If it is not going to provide the MAC address, if it is not going to act like I'm the 20, then R1 will not get the MAC address and the packet information will be incomplete. So all the packets will be dropped. Okay. So this was the issue. Again, then finally we came up with a fully specified method. Fully specified static route. In this case, we provided both the information, IP route, network ID, subnet mask. Then we gave up the exit interface. So exit interface will always be coming first. And then finally next hop. Clear? Then default route, we configured a default route towards one router. Means for all the networks, all the possible networks, we direct the traffic towards the next hop. That's it. We do not care about the destination networks. Then we saw about RIP. So RIP, it is a distance vector protocol. So we saw about RIP. Your RIP is a distance vector protocol. Okay. And your RIP has 2 versions, RIP version 1 and RIP version 2. First of all, your RIP is obsolete, not used anymore. Why? Because it is a purely distance vector and it cannot be applied. It cannot be applied to larger networks. Why? Because it uses the hop count metric. Okay. And the maximum hop count limit of your RIP is 15. Means if there is a network that is 16 hops away, beyond 16 routers, your RIP is not able to provide communication. Okay. For RIP, it is unreachable. Okay. Then it is having 2 versions. Your version 1, it is classful. This is classless. It uses broadcast messages to exchange the routing update. It uses the multicast. It uses the address 255.255.255, and your RIP version 2 uses 224.009. Okay. Then your RIP version 1 does not support authentication, but your RIP version 2 supports authentication. Okay, these are some of the differences. So even when RIP was used, RIP version 2 was only used, RIP version 1 was not used. The basic configuration was you just go to the global configuration mode and say router RIP. Then you just provide the directly connected network and network ID. And this network ID should be directly connected. Log that. Okay, is it clear? Authentication means, let's say we are having two routers. So if I configure RIP on R1 as well as on R2, on both the routers, if I configure RIP, they are going to exchange the updates without any verification. If that, let's say R1 is not going to verify whether R2 is the correct router, I want to share the information. R2 is not going to verify if R1 is the correct router, I'm going to share the information. So what if somebody else coming to your network just connect the router and configure RIP? They are going to share the updates, right? For security purpose, you are going to configure authentication. Means you are going to configure a password on R1, let's say 1234, and same password you are going to configure on R2. Now, before exchanging the update, they are going to match this password. So if the password is matching, they'll share the update. Otherwise, they'll not share the update. Okay. So this is how your authentication works. Verification that, okay, this is the correct router I want to communicate with. Clear? Yes, please. Then we saw about EIGRP. So EIGRP is Enhanced Interior Gateway Routing Protocol. So it is a hybrid protocol. How hybrid protocol? Because it has the features of both distance vector as well as link state. Okay. Then your EIGRP, it uses certain matrices. Okay. Like bandwidth, load, delay, reliability, and MTU. These are the different matrices, and they are written in the K values. Your bandwidth is the K1, load is the K2, delay is the K3, this is K4, and this is K5. By default, your EIGRP is using only bandwidth and delay, but you can configure it in such a way that it is going to use all 5. That is up to you. Okay. Then your EIGRP, it uses the multicast address 224.0.0.10 to multicast the routing updates to communicate with each other. Okay. Then AD value. So it uses 2 AD value. One is the 90 and second is the 170. 90 for internal routes and 170 for external routes. Okay. This was the introduction. And we saw about EIGRP packet types also, that it has hello packet, it has update packet, it has query packet, it has reply packet, and acknowledgement packet. So hello packet, with the help of hello packet, the two routers, if you are having two routers, they will communicate with each other and they will know if the second router is available or not. Means with the help of hello packet, they are going to form a neighborship. Okay. Once the neighborship is formed, they are going to exchange their databases. Once the neighborship has been formed, they are going to exchange their databases. Okay. Very good. Let's wait for a while. There is electricity problem. So we saw about your EIGRP packet types. First is the hello packet, used to form the neighborship. Second, we have the update packet. So with the help of update packet, they are going to exchange their databases. Okay. These two routers, they are going to inform each other about the routes they know, right? Now, let's say they are already having the routes. R1 has the routes about R1 and R2. R2 has the routes about R1 and R2. Means they are having all the possible routes. Now, at some point of time, let's say one route on R1 side goes down. Okay. So R1 is going to ask R2 if R2 has a possible way to reach that network. So it is going to make a query that, do you have that network? Do you have any information about that network? Then R2 is going to reply this thing with the reply packet. So when a network goes down, a router is going to make a query to the other routers, to its neighbors, whether they have a possible way to reach them. Okay. So the neighbors, they are going to reply with a reply packet. And your EIGRP, it is a reliable protocol. So there is an acknowledgement for all the update, query, and reply packets. Means if R1 is sending an update, R2 is going to acknowledge the, okay, I have received your update. If R1 is sending a query, so before replying, it is going to send an acknowledgement that, okay, I have received your query. And if R2 is replying the query, then R1 is going to say, okay, I have received the reply. Okay. So for all update, query, and reply packets, there will be acknowledgement. Clear? Then we started with the OSPF. So let's continue with the OSPF part. So if we talk about OSPF full form is Open Shortest Path First. Okay. Why? Because it is an open standard protocol and it uses SPF algorithm, Shortest Path First algorithm. Then OSPF is a link state protocol. The protocol number is 89 and the AD value of your OSPF is 110. Then your OSPF uses two multicast addresses. One is the 224.0.0.5 and second is the 224.0.0.6. These are the two multicast addresses used by the OSPF. So 224.0.0.5, this is used when the traffic is going for all OSPF routers. and 224006, it is used when the traffic is going for the DR or VDR. Then OSPF uses Dijkstra's algorithm. The complete name is Dijkstra's SPF algorithm. Dijkstra's shortest path first algorithm. Okay. Then your OSPF uses the area concept. Why? To divide the autonomous system into smaller parts for faster conversions. Okay. And it uses process ID. Like your EIGRP uses ASN numbers. For configuration, your OSPF uses process IDs. Okay. Then it uses DR and BDR concept, and your OSPF is a classless protocol and supports subnetting, VLSM and CIDR. Clear? So this was the introduction. The configuration part we saw yesterday. For EIGRP, it was router, EIGRP, and you gave the ASN number. And this ASN number has to be same on all the routers. Okay. Why? Because your EIGRP, it is an IGP protocol, interior gateway protocol. Okay. Then your IGPs, they provide communication in the same AS only. So if you change the AS, your EIGRP will not be able to provide the communication. Okay. Why? Because EIGRP is a type of IGP protocol, and it is going to provide communication in the same AS. Then you give the network, then the network ID, then you give the wildcard. And how do you calculate the wildcard? From 4 times 255, just subtract your subnet mask, whatever your subnet mask is. And this will give you what? Your wildcard. Correct? Okay. And for OSPF configuration, we saw router, OSPF, and you give the process ID. Then you give the network ID. You give the wildcard. Then you said area, and finally area ID. Whatever area your network is in, your router is in. Okay. Now in your OSPF, there are total 7 neighbor states. Means before becoming neighbor, if there are 2 routers. So before becoming neighbor, what they are going to do, they are going to transit from 7 states. Before becoming full neighbor, they are going to transit in 7 states. First is the down and final state is the full. Means when you see a state is full, means their databases are fully synchronized. These 2 routers have all the information about all the routes. Okay. So they are going to start from the down state and go until the full state. Clear? Okay. So first state is the down. Down state means you can say like OSPF is not there on that particular interface. You haven't applied OSPF. Let's say this is Z0 by 0. This is Z0 by 0. Okay. So if you have started OSPF, but let's say you in your router, you gave the command router OSPF 1. OSPF process has been started in your router, but there is no interface where OSPF can send hello packets. So means your neighborship state is down, administratively down state. Then let's say you gave a command and you gave this network 12.0. So what will happen? Your OSPF will send a hello packet this side. Okay. Your OSPF will send a hello packet this side. And as soon as it sends a hello, this state will change to init, means initialization state. Okay. Then you configure OSPF on R2 as well. So your R2 is also going to send a hello packet. So first of all, R2 has received the hello and now R2 has sent. So as soon as R2 is going to send this hello packet, it is going to change the state to init, and it has also received. So instantly it will change to two-way. When you send the hello packet, that is init state. And when you send and receive the hello packet, that is two-way state. Means bidirectional communication has been established. Similarly, when this hello packet reaches your R1, this will also change the state to two-way. Change the state. Now they are going to start sending the databases. Okay. So initially your R1, it is going to send an empty database description packet, DBD, database description packet. These are the 5 packet types. Hello, database description, link state request, link state update, and link state acknowledgements. In short, hello, DBD, LSR, LSU, LSAC. Okay. R1 is going to send a hello packet, database description packet. R2 is going to acknowledge this packet, first of all, that okay, I have received. Second thing, it is also going to send an empty database description packet, and R1 is going to acknowledge. So in this database description packet, they are going to send information about each other. This is my router ID, okay, and these are my IP addresses, like this. So they are going to compare each other's information, and they are going to decide who will be the DR. Okay, DR-BDR concept we haven't discussed here. Okay, after this we'll be discussing DR-BDR concept, but just understand, in this state, two-way state, they are going to compare each other's information. Okay, whatever information is there in the hello packets, they are going to compare and they are going to decide who will be the DR and who will be the BDR. So in the two-way state only, your DR BDR election will take place. Okay, just remember, in the two-way state, your DR and BDR election will take place. Then they have sent the database packets. Now in the database packet, again they are going to compare. Why they are going to compare? Because they are going to see, or they are going to decide who will send the database first, who will start sending the information first. Okay, so in this state when they are sending this empty database, this is known as X start, means they are preparing to start the exchange of databases. They are preparing to start the exchange of databases. So this state will be X start state when they are sending empty databases, and just to decide whether who will actually send the database first. Okay, so the router with the highest router ID, that is going to start sending the database first. Okay, so in this state, in your X start state, there is one more election. Like in your two-way, there is a DR BDR election. So in your X start state, there is a master and slave election. The router with the highest router ID or highest IP, that will become the master, and the master router is going to send the database first. Okay, so they will decide who will send the database first. Once decided, they will actually start sending the database, the DBD. They will actually exchange the databases, and this state will become exchange. Now they are actually exchanging the database. Once they are done with the exchange of databases, now they are going to look into the database, because R1 is going to form their own database with the new information. R2 is going to form their own database with the new information. They have their own databases now. Now they are going to check about which network I'm having the information and about which network I'm not having the information. Okay, so if R1 is not having information about a particular network, then R1 is going to make a request to R2 that I do not know about this particular network. You give me more information about this, and that request packet will be your link state request, that provide me more information about this particular link. Okay, then it is going to send LSR, link state, and your R2, it is going to reply the LSR with the help of LSU, link state update, means it is going to provide more updated information. Okay, and when they are exchanging this LSR and LSU, this state will be loading. Okay, when they are exchanging their LSR and LSU, this state is the loading. And once they are having full information about all the routes in the database, that state will come as full. This is the full state where the databases will be fully synchronized on both the routers. Means both the routers will have information about all the routes in the network. Is it clear? Yes? Any doubt? No? Online people? Okay. Now with the same example, you might have understood about the OSPF packets also. First is the hello packet, used to discover neighbors and form neighborship. Correct? And database description packet, it is used to exchange the databases. Routers are going to use this packet to exchange the databases. Link state request, if a router is not having information about a particular link, it is going to ask more information to its neighbor, and it is going to use the link state request packet. Then the neighbor is going to reply the link state request with the help of link state update. And what is link state acknowledgement? Again, your OSPF is also a reliable protocol. So for all the database link state request and link state update, you will be having an acknowledgement. Clear? So your OSPF, it creates three tables. First is the neighbor table. Second is the, you can say, link state database, or topology table we usually call link state database. And the third is routing table. These are the three tables your OSPF forms. Okay. First neighbor table, it is going to have the list of neighboring routers. Which routers are the neighbors? Your link state database, it is going to have information about all the links in the network, all the networks. Okay. And your routing table, it is the collection of best routes. How to reach a network. So best route to that network is in the routing table. Okay. Okay. Now we'll try to capture the neighbor states of your OSPF. R1, R2. (12.0/24). On this side, I'll use the IP 12.1. On this side, I'll use the IP 12.2. On R1 side, I'll have loopback 1.1.1.1/24 and or 11.11.11.11/24. On R2 side, I'll have the loopbacks 2.2.2.2/24 and 22.22.22.22/24. These are the loopbacks I'll be having on these routers. and we consider that this entire network is in the area 0. Now for the configuration, I'll just use the notepad for easy configuration. Enable configure terminal, and I'll set the host name to R1. Then I'll say interface Z0 by 0, IP address 192.168.12.1, 255.255.255.0 and no shutdown. Interface loopback 1, IP address 1.1.1.1, 255.255.255.0. Just copy this, paste. Interface loopback 2, 11, 11, 11, 11. Done. Copy this. Next configuration is for R2. So host name will be R2. Interface IP will be 2. And this will be 2.2.2.2. 22.22.22.22. Clear? Configuration is done. Just need to copy paste. So copy this configuration. Go to the router. CLI. User execution mode. Paste. Copy R2. Paste. Done. So basic IP configuration has been done. Now we will configure the OSPF. Okay. So I'll say to configure OSPF, global configuration mode, and I'll say router OSPF 1. Process ID randomly I can choose any. Okay. And it can be different on all the routers. So I'll say router OSPF 1. Okay. Router spelling mistake. Then you can provide network and network ID we have to provide. So what are the networks connected? 1.1.1.0, 0, 0, 0, 255. And in which area? 0. Similarly, we have 11. Okay. Area 0. Okay. All right. Next network is network 12.0, 0, 0, 0, 255 and area 0. Done. So R1 configuration is done. Let's go to R2. So I'll say router OSPF 1 network 192. Oh, not this first. I'll say 2.2.2.0 slash wildcard, then area 0. And we'll say 22. Done. Now before configuring 12.0 network, I'll go to the simulation mode because this is packet tracer and is going to work instantly. So if I give this network first, it is going to directly get into the neighbor states. So to capture the packets, we are going to go to the simulation mode. And instead of capturing all the packets, I'll just capture OSPF packets. So I'll just select OSPF. Now I'll go to the router and say network 192.168.12.0, 0.0.0.255 and area 0. If you see a packet has been generated, this is a OSPF packet. And what type packet it is? OSPF hello packet. Correct. Right now, if I go on these routers and check what is the neighbor state, if on R1 I say show IP OSPF neighbor, nothing. So this is the down state when there is no neighbor. Okay. Now this packet has reached here. Okay. Check again. Which state? Do you see? In its state. Okay. So it has received the hello packet. Now it is going to send the hello packet. This is again the hello packet sent. Again check. Again in it. Okay. They're still going to exchange some packets. What about this router? Show IP OSPF neighbor. Oh, directly extract. So they have skipped the two-way state. Okay. This is the packet tracer issue. So now if you see again OSPF hello packet. What is this? OSPF database packet. So they are going to send this database packet. And in the database packet, you will see there is a information like router ID, what is the area ID. These are the informations, nothing else. Okay. Next, what is this new packet? Again, OSPF database. Check the state on this router. Okay, it is still in its state. So database packet is there. Now again, R2 is R1 is going to send database because they are going to share databases, right? And check the state. They have done the election, you see here. This has become BDR. And if you check this router, this has become DR. This is also OSPF database. So in this database, it is going to tell its own router ID, area ID. And this particular packet, it is also OSPF database. So now they are going to exchange the databases, right? See here, they are exchanging the information about the routes. 11. We have a network right this side. So they are going to exchange this information, the database information. These packets are going to go to R2. R2 is going to acknowledge them. Okay, still sending the database. R2 is going to send its own database about the 22. Okay, and check the state. Still exchange state. Why? Because LSR and LSU, they are not yet sending. When they'll start sending the LSR and LSU packet, this state will change to loading. Okay. This is again database. Again database. Now a new packet has been generated. And this is, you see, if you see this side, OSPF LSR packet. Now R1 is making a request. Okay. R1 made a request and R2 also making a request. You see, now they are going to reply the request with the update, link state update. Okay. Similarly, this side also. Now, once the updates have been exchanged, so this state will be, you see, okay, they are already in the full. I forgot to show you before. They were exchanging LSR, LSU, that state was loading. I think I can go back. If I check, no, already full. Okay. So you'll see before it came to the loading state and then it transited to full state. Clear? So this is how your two routers become full neighbors. From down state to full state, they transit total 7 states. And final state is the full. Clear? Then these are the 5 packet types. We saw hello, database, link state request, update, and acknowledgement. Okay. Next, we have the DR and BDR election. Before DR and BDR election, we'll see about router ID. In your OSPF, all the routers, they are identified with the router ID. In the databases also, you saw they were advertising their router ID, right? So what is this router ID? So ID, again, ID is an identification only. Okay, so in your OSPF, if you want to identify the routers, you are going to use router ID. Correct? Now this router ID, it has certain criteria to generate a router ID or select a router ID. A router uses certain criteria. What are the criteria? The first criteria is you can manually set. You can manually set a router ID. Second, if you do not manually set, your router is going to check the loopback interfaces and the highest IP of any loopback interface. That will become your router ID. The highest IP of any loopback interface is going to become your router ID. Let's say you don't have loopback interfaces also. So what in that case? So in that case, the highest IP of any interface, any physical interface, the highest IP of any physical interface will become your router ID. So in this scenario, if you see, what should be the router ID of R1? See, the first criteria is you set manually. You give command to set the router ID. Second will be the highest IP of loopback interface. And the third criteria is highest IP of physical interface. So for looking at this criteria, what should be the router ID for R1? Why 1.1.1? See, we haven't set manually. We didn't set. Second criteria will be highest IP of loopback. So we are having 2 loopbacks. One is 1.1.1.1 and second is 11.11.11.11. So which is the higher? 11. So router ID for R1 will be 11.11.11.11. Correct? What about R2? 22. 22, 22, 22. What if I'm not having the loopback? What will be the router ID of R2? 12.2. R2 is having the IP 12.2, right? So the router ID will be 12.2 because we haven't set manually, we are not having the loopback interfaces. Then the third criteria will come into picture. That is highest IP of any physical interface. Okay. All right. Now check the router IDs. So if you want to check in your router the running routing protocol, so you can say show IP protocols. And there you'll see that the routing protocol running is OSPF and the process ID is 1. What is the router ID for R1? 11.11.11.11. Okay. And for which networks it is performing the routing? These 3 networks. Correct. And what are the information sources? The router self and the neighbor. Okay. Similarly, you can check show IP OSPF neighbor. This is the neighbor table. So only one neighbor. So you see it is being identified with the router ID. Okay. And physical address is also explained here. So this is the router. Neighbor state is full and it has been elected as a VDR. Okay. And through which interface? Z0 by 0. Clear? This is the neighbor table. If you want to check the OSPF database, you can say show IP OSPF database. And this is the OSPF database, which is having information about all the networks. Okay, all the routers. See, 11, this is the router. 22, this is the router. And who is the DR? 12.1. Okay. All right. Now routing table.
12.1 become a DR because it sends the first data, like first hello packet.
No, DR VDR election actually works on the router ID criteria. We'll discuss. Just let me explain about routing table. Okay. So I'll say show IP route. So this is the routing table. And in the routing table, you see you are having the routes with. So right now, this is showing you all the routes, right? Connected and other routes also. But if you want to see particularly OSPF routes, you can say show IP route OSPF. And this will give you only and only OSPF routes. Okay. So through OSPF, we have 2 routes, that is 2.2.2.2 and 22.22.22. Okay. How to reach them? Via 12.2 and the interface Z0 by 0. Clear? Okay. Now let's move to the DR and BDR election. What is DR and BDR? So generally what happens, let's say in a network, you are having certain routers. So those routers, they are going to communicate with each other. This is called a multi-access network. And in your OSPF, the by default network type is broadcast multi-access, BMA. About network types, you will be studying in your CCNP. Let's say these are the 5 routers. Okay, and you have the IP 10.0.0.1, 10.0.0.2, 10.0.0.4, and 10.0.0.5. These are the 5 routers you are having. Okay, so what will be the router ID for R1? 10.1, only one IP we are having, so that will become automatically the router ID. So for R1, this is the router ID. R2, this is the router ID. 3, 4, and 5, same way. Now, if let's say there is any change or R1, there is any change. Let's say I added one more network 1.1.1.1 on R1. R1 is going to inform its neighbors. So it is going to send a packet. So how many neighbors will be there for R1? 4 neighbors. So it is going to inform R2, R3, R4, and R5. It is going to inform each and every neighbor. Correct? Okay. Now consider scenario. Just one scenario we are considering, that R2 received update from R1. We are not talking about other 3. So R2 will see that, okay, there is some new information I'm having. So R2 is going to update its neighbors. R2 is going to inform its neighbors about the change. So what are the neighbors for R2? But it will not send back to R1, right? Because it has received from the R1. So it is going to inform. Correct. Now R3 also received an update. So it is going to inform. Correct. R4 also received the update. We are just talking about the updates received from the R1 only. We are not talking updates from the R2 or R3. We are just focusing right now on the updates they received from the R1. Okay. Then R4 is going to update. Correct. Similarly, R5 also received update from R1. So it is also going to update its neighbors. So let's say, can you imagine the amount of traffic traveling in your network? That is all total useless traffic. Correct. This is completely useless traffic because the same traffic, the same packets, they are getting exchanged again and again. Okay. So this is not a good scenario or good practice. So for this purpose, to reduce this traffic in your multi-access networks, DR and BDR elections take place. What is a DR? Designated router. Okay. And what is a BDR? Backup designated router, or simply backup DR. Okay, these are the two elections that take place. Simply understand, there is a place, let's say it is a village. Okay, in this village, a lot of people are living. So if all the people, in general, all the people will be equal, right? So who will make decisions for the entire village? If a person is doing something he wants, other person is doing something he wants, and they are fighting. Correct. So for this purpose, there is one person elected for the village who is going to make some decisions. In case of disputes or in case of some special occasions, he is going to make some decisions. And everybody is going to follow his decisions, right? Everybody is going to follow his decisions. So who will be this person? Sarpanch, correct? And all the people in the village, they are going to follow whatever he says. Whatever his decision is, they are going to follow. Similar way, in this network, we are going to elect a DR. We are going to elect a DR. So all other routers, they will agree first that who will be the DR, because it is not something random. It happens by election. And the election criteria for DR, it is, first of all, highest router ID. First of all, highest priority. First of all, it is highest priority. And if priority is equal, then highest router ID will be the DR. Highest router ID will become the DR. So the default priority of all OSPF routers, it is 1. So by default in the village, all peoples are treated equally. Everyone is equal. Now how we decide who will be the Sarpanch, who will be the DR of our network? So that will be decided by the highest router ID. So according to our network, which router is having the highest router ID? R5. So R5 will become the DR. Now he is the designated router. But there are some cases that your Sarpanch is no more, not available. Who is going to make the decisions? We are having Up Sarpanch, Vice Sarpanch, Vice President. Similarly, we are having a backup DR also. Okay. And this backup DR will be elected again, second highest priority. Okay. And second highest router ID. Again, priority, if you check, all are equal. So second highest router ID, 4, R4. So this will become the BDR. Okay. Now understand. We saw two multicast addresses, 224.0.0.5 and 224.0.0.6. Okay. So this multicast address is used when a traffic is going for all the routers. And this multicast address is used when the traffic is going for DR or BDR. This thing is understood. Now, what is going to happen whenever there is a change in the network? Let's say again, R1 got some new information. There was a new network attached to R1. Now, what your R1 is going to do, it is not going to inform everyone. It is just going to inform the DR and BDR. Means it will send an update to DR as well as BDR. Okay. So in a village, when both persons are available, the Sarpanch and Up Sarpanch, who is going to actually take the decision? Sarpanch is going to take. Similarly, as long as the DR is available, your BDR will always remain silent. It will just accept the update, but nothing else. It is like it will just stay. It will keep itself updated from the information, but it is not going to inform anyone about anything. It is not going to make any decision. Now, rest of the network will be informed by the DR. Your DR is going to inform that this has been the change. There is a new change in the topology. And everyone will accept the information from the DR. Okay. So if you see, your R1 sent the information to which address? 224.0.0.6. Why? Because it has to send only to the DR and BDR. So when R1 updated the information, it was using the destination address 224.0.0.6. And when DR has to inform each and every router, your DR use the multicast address 224.0.0.5. Okay. So your DR and BDR, they listen to both the addresses 224.0.0.5 as well as 224.0.0.6 and your all other routers. So the routers that are not DR, not BDR, they are known as DR other. These routers listens to only one address, that is 224.0.0.5. So if some information is being sent on 224.0.0.6, only DR and BDR is going to listen. And if some information is delivered on 224.0.0.5, DR, BDR as well as all other routers will listen to that information. Clear? So this is how your DR, BDR election takes place. Clear? Criteria: highest priority and then highest router ID. Yes.
So, as you said that when the R1 receives some new data, to DR.
Yes.
So then DR will broadcast it to
Multicast.
Multicast it to all other routers.
Exactly.
So in that case, already BDR and R1 already has the data because R1 is the one which sends the data. Then is it necessary for it to receive this?
See, the thing is, they are part of the same multicast group.
Correct.
So if you give me some information and if I drop in our class group, still you are getting the information.
Yes.
This is the same thing because you are part of that group.
Yes. But
in multicast, what happens? See, we cannot select people. Everyone who is in the group, multicast group, they will receive the information. Everyone who is in the multicast group, they will receive the information. Okay, no matter they already have it. Okay, clear? Any doubt?
DR, BDR, both down.
In that case, new DR, BDR election. 3 will be the DR, 2 will be the BDR. Same criteria. See, if BDR is bound, let's say DR is there, BDR is down. So new BDR election will be there. BDR is there, DR is down. So BDR will become DR and new BDR election will be there.
So if that happens, then it will again get increased, right?
No.
Because see,
just once they will see. The thing is, they will still agree. They are continuously sending hello packets, right? In OSPF, your routers are continuously sending hello packets. So they are aware of all the routers. So they'll just instantly calculate a new DR and BDR.
Once the OSPF installed, it is done by itself only.
Yes, DR, BDR election completely itself. You can alter the DR, BDR election by changing the priority. We'll use the comments.
sir, the priority is set manually. So
by default, it is 1. You can change it.
no, but usually the priority is set manually, and according to the priority, which has the highest priority level, that will be the one.
Yeah, I'm saying by default, the priority is 1, but you can change it. This is the by default case I'm explaining. Now, to alter the DR, BDR election, we can change the priority. Okay, is it clear? Okay, let's go for the practical for DR, BDR. And again, your packet tracer sometimes create an issue in the DR, BDR also. Let's say I'm configuring router R1 first. So your packet tracer is going to make R1 as the DR. Okay, so let's take 5 routers. Same scenario we'll use. This will be 10.0.0.1, 10.0.0.2, 10.0.0.3, 10.0.0.4, 10.0.0.5. And for configuration, I'll again use packet, not packet. So R1 is 10.0.0.1, not having the loopbacks. 10.0.0.2, 10.0.0.3, 10.0.0.4, and 10.0.0.5. This is clear. Now we are going to configure OSPF also. So we are considering entire network in area 0. So I'll say router OSPF 1. How to set the router ID manually? You can set like command is router ID and you give the router ID like 1.1.1.1. Like this, you can set manual router ID. Okay, so your router ID will be in the format of 32-bit IPv4 format. Okay, this is how you can set. And your router ID, whatever IP you use in the router ID, that need not to be available on the router. Let's say we are not having 1.1.1.1 on the router, right? R1, we are not having this IP. So you can still use this IP. Okay, but right now I'm not assigning. We are going with the default router ID. And then you can say network 10.0.0.0.0.000.255 and area 0. Complete configuration. That's it. Same configuration everywhere. Because all are in the same network. Correct? Now I'll just copy and paste. Say no. Paste. Done. Okay. Let's go on R1 and check the neighbors of R1. So I'll say show IP OSPF neighbors. See 10005 highest router ID DR. 10004 second highest router ID BDR. And remaining all the routers, they will be DR others. DR other means not DR, not BDR. The routers that are not the DR, not the BDR, they will be DR others. Then second thing you must note, what is the neighborship state? Again, what is the neighborship state? But with the DR others, two-way. So if you remember the neighborship states, the first state when they send the hello packet is the init, correct? And when they have also received the hello packet, it is two-way. So it is not going beyond that. It is stuck on the two-way only. Means these routers, DR others, they will not be able to exchange the databases. They will not be able to exchange the databases. Means R1 cannot directly provide any information to R2 or R3. R1 has to provide the information only to R4 and R5. Okay, this is clear. So what is going to happen? See, your DR is going to form, means your DR and BDR, they will form a full neighborship. Your DR with the DR others going to form full neighborship. Okay, your BDR and DR is going to form full neighborship. Your BDR with DR others going to form full neighborship. But your DR others with other DR others going to form two-way. Means the DR other routers, they will not be able to exchange any information with each other. They can only exchange the information either with the DR or with the BDR. But the DR and BDR, they can exchange to everyone.
They only exchange the hello packet.
Only the hello packets, just to be sure that, okay, they are alive. They are alive, they are in the network. That's it. Okay. Is it clear? Okay. Now we'll see what happens when we attach one more network on R1. So I'll go to R1. I'll say configure terminal. Interface loopback 1. I'll say IP address 1.1.1.1 255.255.255.0. Okay. Now before advertising this particular network in the OSPF, I'll go to the simulation mode so we can capture the packets. Okay. So again, I'll say router OSPF 1. I'll say network 1.1.1.0 0.0.0.255 area 0. And before hitting enter, I'll just go to the simulation mode. And now if I advertise this route, you'll see R1 has generated a packet. In this packet, if you see the information, what kind of information is this? What is the destination IP address?
Destination is 224.06.
224.0.0.6 means this packet is going to go to the DR as well as the BDR. Okay. Now you switch understand multicast. Okay. You switch understand multicast. So it is going to forward to 3 and 4 also. I mean 2 and 3 also. But they do not listen to the 224.0.0.6 address. So they are going to drop this packet. Okay. So see here. Came to the switch. Went to everyone. They are going to drop. And your DR and BDR, they are going to accept. Now, see, the information has to reach the DR. The BDR will remain silent and the DR, it is going to inform everyone. How it is going to inform everyone? If you open this packet, see what is the destination address. 224.0.0.5. Okay. Now, everyone in the network is going to receive this information. And you'll see everyone has accepted the information. Why? Because it has been sent by the DR. Okay. And they are going to acknowledge it. That, okay, we have received. So you'll see this is an OSPF acknowledgement. Correct? And this is how your DR and BDR works. And if there is some change, again, let's say if there is some change on DR or BDR, they are going to directly advertise on the address 224.0.0.5. 224.0.0.5 because they have to inform everyone. The neighborship of your DR and BDR, if you go and check, it is full with everyone. This is the BDR. So do show IP OSPF neighbors. All are full. And what is the default priority here? 1. Okay. Similarly, your DR also has all the full. Do show IP OSPF neighbor. So DR and BDR, if there is change on DR and BDR, they are directly going to advertise on 224.0.0.5. So let me add one more route on the 10.0.0.4. So I'll say interface loopback 1. I'll say IP address 4.4.4.4 255.255.255.0. Then I'll say router OSPF 1 network 4.4.4.0.0.0.0.255 and area 0. Before hitting enter, I will go to the simulation mode. Hit enter. Packet has been generated. Now this particular packet, you see, 224.0.0.5, because it is destined for all the devices in the network. And everyone is accepting. Understood? Any doubt? So this is your DR and BDR concept. So any doubt in this part? Now with OSPF, we have one more small concept. So let me discuss it today only. We have, this is just small concept about LSDB and LSA. Okay. So what is LSDB? LSDB stands for link state database. Okay. It means when the OSPF routers, they are exchanging the information, they are exchanging the database packets, they are creating their database, and we can check the database with the command show IP OSPF database. Okay. So right now in your syllabus, we are only having single area OSPF. Okay. We are only having single area OSPF. So in single area OSPF, we have two types of LSA. Okay. In your OSPF, there are total 7 LSAs, but when we consider only single area, then only 2 type of LSAs are in use, the type 1 and type 2. Your type 1, it is known as router LSA, and type 2, it is known as network LSA. LSA means link state advertisement, means the update they are saving. So the router LSA, it is generated by all the routers in your area. Router LSA, it is generated by all the routers in an area. Okay. While your network LSA, it is generated only by your DR. And these LSAs, they are forwarded within an area only. They are not going outside the area. Okay. So means if in a DR-BDR concept, if I check, if I give the command show IP OSPF database on all the routers. So in the type 1, I'm going to find the information about R1, R2, R3, R4, and R5. But when I check the type 2, who is the DR? R5. So we'll find the information about R5. Okay. So let's check. If I go to R1 and say, do show IP OSPF database. Sorry. Clear? They are having all the information. So in the router link state means type 1 LSA, you will have information about all the routers in the area. And in the network LSA, you will have information about the DR. Similarly, if you go and check on R2, you will find the same information because in one area, the database of all the routers is the same. Show IP OSPF database. Again, spelling mistake. Same. Correct. Go and check on R3. It is the same. Show IP OSPF database. Same. So in one area, all the routers will have the same database. Do show IP OSPF database. Again, same. Total 7 types you will be studying in your CCNP only because you have there your multi-area also. Okay, virtual link concept also. Yes, because area concept is just to divide the autonomous system into smaller parts so that your routers can converge fastly, means the network information, the route information can travel fastly. They can fastly prepare the database and start working. Okay. Area is manually configured. Like we decide, okay, these many routers, they are in the area 1, area 0, this kind of condition. Okay. So all routers will be having the same database. Yeah, according to that, there will be the DR-BDR election. But again, there is one more thing. See, when you give the command router OSPF 1, then if you provide the networks first, let's say network this, network this, network this, network this. You provided the network, router has already selected the router ID automatically. Okay. So if you want to manually specify a router ID, always specify just after this command. Otherwise, if you are specifying the router ID, let's say at the end, then your router will tell you that this router is not applicable. This router ID is not applicable. You have to run a command clear IP OSPF process. When you run this command, entire OSPF calculation will be again, and then new router ID, whatever router ID you have specified, that will be applicable. Like in our current scenario, you see, if I check on R1, so on R1, we are having a loopback 1.1.1.1. So according to our router ID calculation, what should be the router ID? Loopback IP 1.1.1.1. Because first of all, manual will be checked. Manual is not there, then the loopback will be checked, correct? And if loopback is not there, then the highest IP of interface will be checked. So initially, when we performed, when we configured OSPF, this was selected as the router ID. You can check. Do show IP protocol. What is the router ID? 10.0.0.1. But still, we are having loopback, right? So if I say do clear IP OSPF process, and if I say yes, okay, it will recalculate all the yes OSPF. And now you check do show IP protocols. Again, show IP interface brief. Okay, loopback is there. Do show IP protocol. Should be 1.1.1.1. Clear IP OSPF process. To show IP protocol. Show IP protocol. Okay, this is just a bug. So you go router OSPF 1, and now let's say you set manual ID. Right now we are having 10.0.0.1. This is just a bug. It should be 1.1.1.1. Your loopback IP will always be considered as your router ID. Okay. So let's say I'm trying to set 11.11.11.11. Random. Hit enter. Your router is going to say reload or use the command clear IP OSPF process command for this to take effect. Otherwise, this will not take effect. And if you clear the IP OSPF process, do clear IP OSPF process. Now let's check. Do show IP protocol. Is there? Yes. So if you are manually, if you want to manually change it, either specify just after the router OSPF command. Okay. So you don't have to give this clear IP OSPF process command. And if you are giving the command late, then you have to clear the process or you reload your router. That's clear. Any more doubts? No? Anyone? Online people?
Show us like how exactly the manual process changes the
Manual process to change the DR and we can see. Okay, one more extra concept. So do show IP OSPF neighbor. Right now, okay, I'm on R1. How come this become?
because we have given
11.11.11.11. Okay, so right now we already changed the DR by changing the router ID. Okay, so let's go to R2 once, R3. And if I check here, do show IP OSPF neighbor. So who is the DR? Who is the BDR? Let's say I want to make DR the 10.0.0.2. So I'll just change the priority. Okay, I'll just go and change the priority. By default priority is 1. So I'll go to the second router and change the priority. So go to the second router, configure terminal, interface Z0/0, IP OSPF priority, and let's say I'm saying it 100. I just increase the priority. Hit enter, then exit and say clear IP OSPF process. Now do say yes.
You can clear the process from any of the router, right? It is not mandatory that we have.
Yes, but some majorly you configure clear on the router, you get the change. Okay, so you see right now this router R2 has made full neighborship with everyone. So from here itself you can know that it has become the DR. But again, let's go to R1 and check, because earlier R1 was the DR, right? If you checked, R1 was the DR. Now you check again. Do show IP OSPF neighbor. Who is the DR? R2 is the DR. So if you want to manually alter the DR BDR election, you change the priority, increase the priority. And if you want that a router should never become a DR BDR, or it should never take a part in DR BDR election, set their priority to 0. They will never take part in the DR BDR election. Okay, this is clear. Any more doubts?
So even the link pair also they will not come.
They will not participate in the election because their priority is 0. Clear?
So for example, if the DR and DDR, one of them is down
Hmm.
and they never come out.
Hmm.
So then the DR will be transferred to the BDR.
No. DR is the highest priority or the highest router ID. That will remain. New BDR will be elected from the remaining. Yes. If your DR goes down, then your BDR comes the DR.
That's the.
But if DR goes down, BDR goes down, your DR never goes to BDR. And new BDR is elected. Let's say we are having the Sarpanch in the village. So if Sarpanch is not there, then your Up Sarpanch is going to make the decisions. Right? But if Up Sarpanch is not there, no effect to the Sarpanch. That's it. This is clear? Any more doubts? Online people?
It's all good.
Okay. So that's all for today. We'll meet tomorrow. Have a good day, guys. Thank you.